In most people's lives, there's an efficiency partition between everyday and esoteric knowledge. After all, to navigate a typical modern life, most people don't need to understand relativity. So in most cases, the goalposts on life's playing field stop at 3 space dimensions and Isaac Newton's worldview of constant space and time. But the goalposts sometimes move, and what we need to know to be able to function moves too. This is one of those times. The recently launched James Webb Space Telescope, which I'll call the Webb in this video, has permanently moved the goalposts, has changed what people need to know to have a reasonable handle on reality. Look at this image taken before the Webb telescope came along. See the blue arc? It's called an Einstein ring. Well, strictly speaking, an Einstein arc, whatever. It's caused by a foreground mass curving the light rays from a background object. Until now, this kind of image was only seen by astronomers and a handful of others, people who understood what the image represents. People who weren't astronomers or scientists wouldn't be likely to see or need to understand an image like this, but the Webb is changing that. Because of the publicity surrounding the Webb, seeing images of large-scale space-time curvature is now an everyday occurrence. What's missing is a context for understanding space-time curvature and what it means about our universe. By the end of this video, you will understand the connection between Einstein rings and gravity, and your own personal goalposts will have moved. As with all my videos, my goal is to contribute to your intellectual toolkit, to upgrade your biological software. Let's get started. Most of my viewers understand a world of 3 dimensions: left, right, up, down, and far, near. Each of the space dimensions lies at right angles to the others. So for example, moving in the left-right dimension doesn't move you in the up-down dimension. These are 3 space dimensions. In this video, I'm going to discuss a 4th dimension, the one we call time. Time is a dimension like left and right, up and down, and like the space dimensions, the time dimension lies at right angles to the others. Well, that's easy to say, but hard to visualize. The time dimension is more intriguing than it may seem at first glance. It gets mixed up with the space dimensions in interesting ways. In this recently released Webb image, the effect of the 4th dimension is clearly visible in the curved light paths near massive objects. This image shows light from a distant galaxy curved around a closer, very large galaxy cluster, so we see the distant galaxies displaced from the positions they would have if the nearby mass were not present. In this close-up view, we see that a relatively nearby massive galaxy cluster, marked by the blue circle, has sufficient mass to curve the light paths of more distant galaxies. The red outlined image at the left shows 2 views of the same distant galaxy. The purple outline at the right shows the same effect, likely also 2 views of a different galaxy, whose separate appearances travel along different paths to Earth. The green outlined object at the upper left is a nearby star, which shows the trademark Webb 6-pointed starburst spikes created by the edges of the telescope's hexagonal mirrors. As before, these curved paths are called Einstein rings, or commonly partial Einstein rings, since they're almost never complete rings. They have this name because they're predicted by Albert Einstein's theories. More on this later. I prefer to call them Einstein arcs, but this terminology isn't commonly used. We know perfect Einstein rings are possible because we can write mathematical models that create them. Here's a video of my most recent Einstein ring model, showing an imaginary black hole making its way from the lower right to the upper left, where it aligns with a distant star cluster to form a perfect ring. The reason we don't often see perfect rings in nature is because A, the focusing masses aren't likely to be point sources like black holes, B, the focused masses aren't likely to be point sources either, and C, such random alignments don't favor our little wandering planet. Also, the idea of a supermassive black hole, separate from a galaxy, wandering around extragalactic space at high speed, as shown in my model, is physically possible, but not very likely. Some may look at these images and say, wait, light beams can change direction? Doesn't that require the speed of light to be different in different places, so some of the light will slow down and allow the beam to curve? The answer is that the speed of light must be constant everywhere, but time can change. If you slow time down in certain places, then light beams can curve while keeping a constant speed, which is defined as distance divided by time. Einstein's relativity theory predicts that time will slow down near masses, and we have lots of evidence confirming this effect, including these telescope images. Before we move on, I have something amazing to tell you, and I hope you're sitting down. Space-time curvature doesn't just deflect light beams by slowing time down. They deflect us too, and all other massive objects. Before Einstein came along, we thought gravity was a force like the ones that hold atoms together, but it turns out gravity isn't a force. It results entirely from space-time curvature. Are you sitting down yet? Okay, whatever. The reason you're attracted to the floor is because time is passing more slowly beneath your feet. Space curvature also plays a part, but in Earth's vicinity, time curvature is the primary effect. If the rate of time passage were suddenly to become the same at the center of the Earth and at the International Space Station, we would all float away. Before exploring four-dimensional space-time, let's examine the three space dimensions. How do we describe celestial bodies? Example, how does Jupiter compare to Earth? On the Wikipedia Jupiter page, they say Jupiter has a radius 11.2 times that of Earth. But on the NASA page, they say more than 1,300 Earths would fit inside Jupiter. How can both these numbers be true at once? The answer is they refer to different things. One refers to length, a one-dimensional measure, and the other refers to volume, a three-dimensional measure. Space measurements are ranked by the names we give their properties: length for one dimension, area for two, and volume for three dimensions. These measurements are also ranked by an exponent we use to compute the quantity we would get when using a one-dimensional argument. For one dimension, the result is called length. The exponent is 1, so the result increases directly as the measured quantity. This is the tautological case, bear with me. For two dimensions, the result is called area. The exponent is 2, so if we uniformly increase all dimensions, area increases as the square of the length of any single dimension. For three dimensions, the result is called volume. The exponent is 3, so if we uniformly increase all dimensions, volume increases as the cube of the length of any single dimension. To compare Jupiter's volume to that of Earth, we take the ratio of their radii, which is 11.2, compute the cube, meaning multiply the ratio by itself twice, and we have a volume increase of roughly 1,405. This resolves the earlier unequal descriptions of Jupiter and Earth because a planet's volume, a three-dimensional measure, increases as the cube of its radius, a one-dimensional measure. But I have a better down-to-earth example. Let's slice open an avocado. It turns out that because of binocular vision, people see in 3 dimensions, but when processing sensory inputs, we often think in 2 dimensions, sometimes only 1. In this image of a virtual avocado, the pit is 4 centimeters wide, and the entire avocado is 8 centimeters wide. So we have a pit diameter of 4 centimeters and an overall diameter of 8 centimeters, 4 of pit, 4 of avocado. So the pit occupies half the avocado's diameter. What a waste! Why would nature, famous for wasting nothing, design such an inefficient organism, evenly divided between pit and avocado? But before we criticize Mother Nature, let's analyze this by the number of dimensions. For one dimension, a measure of length, the exponent is 1, so the avocado's width is only twice the pit's width. Shockingly wasteful. Half pit, half avocado. For 2 dimension, a measure of area, the exponent is 2, area is length squared, so a sliced avocado's surface area minus the pit is 3 times the pit's surface area. Okay, not so bad. 1 part pit, 3 parts avocado. For 3 dimensions, a measure of volume, the exponent is 3, volume is length cubed. So the avocado's volume minus the pit is 7 times the pit's volume. This means a typical avocado, with a pit spanning half its width, is 87.5% avocado and 12.5% pit. Apparently our eyes deceive us, and it seems Mother Nature designed the avocado better than we thought. Here's an image of the computer avocado drawn entirely as volume cubes, 7 avocado cubes and 1 pit cube. It's easier to see the relative proportions when shown this way. Before I show some pretty space-time animations, let me share a little history. In 1905, Albert Einstein published his first relativity paper, the one we now call special relativity. It deals only with velocities, not accelerations. That came later. In Einstein's 1905 paper was a key equation, the so-called beta equation, similar to the one published by Hendrik Lorentz, but used by Einstein for a different purpose. The beta equation appears at the top of this triangle animation, but if math annoys you, just ignore it. The triangle provides the same information with no math. Now get this. When Hermann Minkowsi, Einstein's math teacher, saw Einstein's paper, he realized it could refer to a 4-dimensional geometry consisting of 3 space dimensions and 1 time dimension. Minkowsi independently developed this idea and later famously said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Minkowsi called it spacetime. Einstein, temporarily left behind by his teacher and others, and somewhat frustrated, said, "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore." But in time, Einstein recovered, developed a better, more general relativity theory, and once his radical ideas were confirmed in empirical tests, he became famous. For our purposes, we can examine the relationship between space and time by drawing a triangle. This triangle's sides represent 3 velocities. Space velocity is red, time velocity is magenta, and light velocity is yellow. Pay particular attention to the yellow side of the triangle marked C, which refers to the speed of light. Because relativity requires the speed of light be constant, the triangle's hypotenuse, the yellow side, must have a constant length. The other 2 sides can change length from 0 to a length equal to the speed of light. Now imagine you're watching a nearby spacecraft that is stationary relative to your craft. In this example, the space velocity is 0, therefore the time velocity is equal to c, the speed of light. Does this mean at 0 space velocity, the speed of time is equal to the speed of light? Yep, that's what it means. As slow as things may seem at times, in a stationary frame of reference, time moves at the speed of light. Now imagine the observed spacecraft begins to move. Let's say the other craft gets to 25% of the speed of light, a speed no earthly craft has yet achieved. If you were able to observe events on board the other craft, you would see time passing at 97% of your own craft's time. But remember, in relativity, everything is relative, so observers on the other craft would see your time appear to slow by the same amount. Now imagine we design much better spacecraft engines than we have now, engines that can accelerate a spacecraft for days, years, centuries, without running out of fuel. Couldn't we accelerate past the speed of light? Well, no, because as we approach the speed of light, an observer on a separate craft would see an apparent and boundless mass increase on the observed craft, because mass is defined in terms of time, and time velocity is slowing to 0. And most important, if we could somehow get to the speed of light, time would stop. This means photons, the carrier particles of the electromagnetic field, must have 0 mass and don't experience time. The space-time triangle delivers a clear message. If you move fast through space, you move slowly through time. And if you could somehow move at c, the ultimate speed limit, time would stop. To summarize this section, Einstein crafted a theory that implied four-dimensional spacetime, but Einstein himself missed the implication. Others filled in the blanks. In this section, I describe old and new optical methods. In the old optics, which dates to the 17th century and Galileo, people exploited the discovery that glass bent light rays. We didn't understand why glass bent light until recently, but as with many breakthroughs, we exploited an effect we didn't understand and waited for science to catch up. Now we know that glass bends light by changing its velocity, by slowing it down or speeding it up. This doesn't violate the constant speed of light, because glossing over some technical details, glass slows light down by making it take a longer trip at its natural velocity. Glass lenses work by redirecting light in such a way that all the rays from a specific source are deflected to a particular location on a sensor or our eye's retinas. Lenses exploit velocity changes, faster or slower, in a way that causes the light wavefront to change direction, and that effect relies on the angle between the lens surface and the wavefront. In this animation, we see that because of the angle between the wavefront and the glass surface, some light rays change speed before others. And like a row of marching soldiers, this selective speed change causes the row to change direction. It's important to say that all important optical effects take place at the surface of lenses, where light is being slowed down or sped up, either of which causes a change in light's direction. Lens design has evolved into an art form as well as a science, and modern cameras rely on clever designs and a deep understanding of optical materials. That explains old optics. The new optics, based on space-time curvature, has been observed for some decades by a handful of astronomers, but not so much by the public. The new optics is becoming public knowledge because of the Webb telescope's dramatic images, many of which show more space-time curvature than even astronomers expected. In the new optics, and unlike the old, we can observe the process, but we can't control it. The new optics is very useful to science. For example, it can brighten the light from a distant object as a mass passes in front of it, in circumstances where we may not be able to directly image either the light source or the focusing mass. It can quantify mass concentrations that would otherwise require guesswork and provide observational support for some difficult theories. For example, in our search for dark matter, space-time curvature reveals where dark matter is concentrated, matter that is otherwise notoriously unobservable. In this animation, based on my space-time curvature model, we see the effect of changing mass on light, and we see how space-time curvature differs from traditional glass optics, how space-time curvature can produce an Einstein ring but cannot produce a camera-style image. The rainbow of colors near the center of this animation shows the amount of curvature near the focusing mass. It's important to say that once light rays curve past 90 degrees, the central mass either is, or may soon become, a black hole, with light perpetually orbiting near the black hole's event horizon. It's interesting to speculate what would have happened if we had observed space-time curvature before Einstein's theories explained and predicted it. It would have been like our present reactions to dark matter and dark energy, two phenomena for which so far we have no theories at all. Here's an orbital model I wrote as part of my Webb telescope studies. The Webb telescope orbits something called a Lagrange-point, a point having no net gravitational accelerations, which means a spacecraft can dwell there with only small energy expenditures. NASA chose Lagrange-point L2, located 1.5 million kilometers from Earth. NASA chose this distant location because it keeps the Webb out of the shadows of both the Earth and Moon, giving it a better view of the space beyond. The craft must orbit the Lagrange point to avoid sitting directly on the Earth-Sun axis, where the Sun's radio energy would blind the spacecraft to communications from Earth. In what follows, remember, to be able to track the Webb telescope's orbit, this animation's viewpoint must rotate along with Earth's orbit, That's why the background stars are moving. This means the real orbital path taken by the Webb telescope is more complicated than this simulation reveals. A short digression into theory. Lagrange points don't attract masses. They aren't cosmic vacuum cleaners. But a mass located at a Lagrange point won't experience repelling forces either. Over time, a mass will drift away from the point because of unexpected real-world forces like solar wind or the occasional micrometeorite impact. This means a spacecraft located at a Lagrange point is like a pencil balanced on its tip. Therefore, to stay at the point, over time a craft must expend some fuel. This is called station keeping. To make things more interesting, some Lagrange points show a net gravitational attraction in one spatial dimension, but no attraction in another. This makes it possible to orbit a Lagrange point as though it was a planet, but only if the orbit is chosen carefully. In this simulation, I launched my mathematical spacecraft, approached the target Lagrange point, then applied an initial orbital velocity chosen to create a long-term stable orbit. What I discovered was that a stable Webb telescope orbit relied very much on an exact initial velocity value, and that value had to be determined by experiment, not by an advanced theoretical calculation. I used a classic computer technique called a binary search to acquire the optimal orbital velocity, and for a stable orbit, I found the initial value had to be accurate to, wait for it, 10 decimal places. I found that if the velocity value was wrong by a small change in the 10th decimal place, the orbit would fail and Webb would drift away. That means this orbit meets the formal definition of a chaotic system, a system extremely sensitive to initial conditions. After optimization, my model spacecraft can orbit the target Lagrange point for 24 months with no fuel expenditure, but only if the initial velocity is chosen with exquisite precision. It's important to say this kind of modeling is useful to establish and test theories, as well as being entertaining, but it has little value in an actual space mission, where the delicate orbital balance will surely be disrupted by a change in the solar wind, or a micrometeorite impact, or some other disruption. Over time, these unpredictable real-world forces require small fuel expenditures to keep the craft on station. Notice in this second perspective view that the Webb orbit is tilted away from the vertical orientation one would expect from conventional orbital theory. This results from the fact that Webb's 6-month vertical orbit is being carried along by Earth's 12-month horizontal orbit, and Earth's orbital motion twists the Webb's orbital plane away from the vertical. Interestingly, if the Webb orbit's direction of rotation is reversed, the tilt reverses also. In this close-up view, notice the wobble in the orbital path toward and away from the Moon's orbit. This is caused by the Moon's gravitational effect on the spacecraft. This represents yet another confounding issue in stabilizing this difficult orbit. People who spend time in Alaska know that black bears like to stay near food stores. As it happens, what's true for black bears is true for black holes. They also like to stay near their food source, which is nearby stars. Unlike my earlier imaginary free space wandering black hole, real supermassive black holes tend to be found at the center of galaxies, where they chow down on any stars that get too close. Our galaxy, the Milky Way, has a supermassive black hole near its center, and we've recently gotten a picture using a worldwide array of radio telescopes as our camera. Our black hole, named Sagittarius A star, or Sag A star if you want to sound like an insider, is sort of like a fidgety child. It's in constant dynamic motion with respect to its neighbors. This makes A star a difficult imaging target. It changes appearance too rapidly for long exposures, and there's no fast shutter speed option for our array of synchronized radio telescopes. Consequently, the best images we have are blurred and approximate, smeared out over time compared to what we would get if we actually visited the place, which, given that it's 25,000 light-years away, isn't a realistic goal. Imagine such a voyage anyway. The fastest human spacecraft to date is the Parker Solar Probe, which reached a speed of 163 kilometers per second. At that speed, it would require 46 million years to get to A star, take a picture, and start back. By the time the round trip ended after 92 million years, the human race would be a distant memory. But hey, no problem. To avoid any mortal limitations, we could assign the mission to a robot. And when the robot came back, it would say, "Success! I have perfect pictures of the..." Hello? Where is everybody? Now that the Webb is in orbit and ready for action, Sagittarius A star is on a short list of high-priority targets, because this is the kind of object the Webb was designed for. The black hole is hidden behind clouds of dust near the center of our galaxy. It emits lots of infrared energy, the very wavelengths the Webb was designed to see, and in the Webb's location, there's no earthly atmosphere to limit resolution and spoil the results. Over the past 30 years, before the Webb became available, astronomers have been using ground-based telescopes, the 10-meter Keck telescope in particular, to track the orbits of stars around a star. They did this on realizing those orbits could be used to infer the black hole's mass, which turns out to be about 4.1 million times the mass of our Sun. The task of tracking the stars orbiting a star is a difficult but scientifically important project, and 2 dedicated astronomers have been central to this multi-decade effort. In 2020, one of those astronomers, Professor Andrea Ghez of the University of California, won a Nobel Prize for her work on this project. Professor Ghez is only the 4th woman to win a Nobel Prize in physics. It's widely held that the small number of female Nobel Prize winners results more from systematic bias than the quality of women's scientific work, and that makes this prize all the more important and certainly deserved. I don't know much about the lives of this small group of world-class scientists, but I know that in order to function as individuals and as scientists, they exercise their right to autonomy and self-determination, not as a privilege, but as an inalienable right. I mention this because, in the United States, powerful forces are systematically and deliberately stripping away a woman's long-established right to choose to exercise bodily autonomy in a way that, in terms of human rights, positions the United States below all civilized Western countries. These undemocratic, authoritarian forces have made their goal clear: turn back the clock and move women from the status of citizens to the status of property. They intend to outlaw reproductive rights and choice, family planning assistance, sex education in schools, and compassionate interventions. They're also proposing laws to forbid even talking about these things. If they get everything they want, what I say in this video could become illegal. After these people get everything they say they want, I suspect they'll pass one more law to seal their victory. Women won't be allowed to buy shoes. That way, women will all be barefoot and pregnant, and there will be no more female Nobel Prize winners. It's a sign of the times we live in that a 10-year-old rape victim had to travel to a different state in order to be treated appropriately, fairly, and compassionately. Please think about this. Confronted by the same medical problem, a dog or a cat would receive prompt, appropriate treatment, locally, without question or hesitation, but not a 10-year-old girl, a crime victim. Someone might object that you can't compare a dog to a human, to which I would reply, you must not know any dog owners. This victim's identity is unknown, as it should be, but I can guess what she was thinking during her travels. Am I a human being, or am I property? Please give her your answer. Tell her she matters. Prove to her that she is a human being. Take action now. Register to vote, then vote. Vote these Neanderthals out of office. Thanks for watching. Please like and subscribe. Before I go, one more thing. Did I remember to ask you to vote?